Hello and welcome to lesson 2 of week 12. In this lesson, we are going to discuss topological sort, and then we are going to add the different approaches that we'll use in this class that we have created in the last lesson. Now, when we talk about a directed acyclic graph, it is a graph with nodes connected by directed edges, and it is impossible to start at any node and follow the arrows to loop back to the same node. The directed path means that the connection flow in one direction, and acyclic indicates that there are no circles or loops. Now, when we want to do a topological sort, it is like ordering of the nodes, but we can only do this in a directed acyclic graph tag. And when we do this, we have for every directed edge, so let's say we have U and V. So for every directed edge U to V, U will always come before V. And so we use this in like build systems. We use this to have like course prerequisite planning, to say you have to take this course before you take another. In scheduling, we do that. And when we want to do dependency resolution, we use those things. So how do we implement topological sort? There is something we call the Kahn's algorithm written K-A-H-N, and what we want to do is that we compute the integrity for all vertices, and then we initialize a queue with all 0 in degree node, and then we pop from the queue to add it to the ordering, and we reduce the degree of its neighbors. Any neighbor that becomes 0, we push to the queue. If ordering includes all nodes, is success, else circle is detected. So things like that. So we can implement the topological sort using the Kahn, and we can see another method of doing that using the DFS method. And what we do is add node to stack after exploring all the neighbors, and then we reverse the stack. So let's try to add those different methods here, and we use this to like iterate through or traverse through the nodes, and we are going to do the topological sort. So we are going to add two methods here. Let's say here we want to add a breadth first search. So let's say the breadth first search like this, and we want the self and start. So now we want to set the visited node like we did in last week's lesson. We want to have a unique item set for a unique list of all the nodes that have been visited, so we don't revisit a visited node and end up in a loop without ending. And we want to set the queue. Let's use the queue. So let's import the collections module. So say from collections import the queue. Okay, so let's use the queue. Now for those of you taking Python for data science, we are going to look at some of these modules to make you understand deeply some of the commonly used modules that we'll come across. So we'll say Q is equal to DQ, and we'll DQ from the start, right? Now let's set an empty list for the order. So now I'm going to say while Q, the node will now be equal to Q dot pop left. Then if the node is not in the visited, so if node not in visited, we want to order dot append the node, and then visited dot add the node. And let's get an iterator, and we'll say for the neighbor. So we're doing the same thing we did in the last lesson, in week 11 lesson, where we did the breadth first search. So we'll say for neighbor, let's get a throwaway variable that we'll use in self.graph node. We want to say if that neighbor is not in visited. So let's say if neighbor not in visited, then let's append it to the queue dot append neighbor, and then let's return order at the end. Let me say return order. Let's do the other method of traversing, which is depth first search method, where we add node to stack after we have finished exploring all the neighbors, and then we reverse the stack. So let's do it like this. So say def, let's call it DFS, and here self start. So here what we want to do is we set the visited, we set the order, and then we just want to add to the stack. So we'll say visited is equal to set order is equal to list. Let's have an inner function, the TFS node, and for this we want to say visited.add the node, and then for the order we append the node. Now because order is a list, visited is a set, so we're using the method that we used to add them. So order.append node. Now we say for the neighbor, we use a throwaway variable here in. You can use anything, you can put neighbor I, or you can do it like we did, like you can say for neighbor weight, whatever you want to do there. So I just put for neighbor a throwaway. We don't really need it, we just need to iterate in self.graph node. If the neighbor is not in visited, then we want to recursively call this, right? And then let's say DFS start, and then we return, then let's return the order. So I think this one we'll use breadth first, we use depth first, and then let's use this breadth first search, but let's use the Kahn's algorithm to do the topological sort now. So now, since we're using breadth first, let me say depth topo sort, let's use Kahn, okay, and self. So we want to say, let's create a variable called in degree. Let it fit the definitions that we have. So in degree is equal to, let's say n0 or n in cell dot graph. Then let's say for the node in graph or neighbor in cell dot graph node in degree neighbor does equal 1. Now let's say the q is equal to the q or n in self dot graph if in degree n equal to 0. Now we'll set the topo is equal to this. So now we'll say while the q, let's say node is equal to q dot top left and topo dot append the node here, and then we want to now say or look at the neighbor and update for the neighbors or for the adjacent vertices like we did before. So let's call this neighbor. So for name underscore in self dot graph node, right, in degree neighbor minus equal, so minus equal 1, and if it is equal to 0 then we want to append or add it to the queue. So if in degree neighbor equal to 0, you dot append neighbor. So let's say if the length of the ordering here now of the topology is not equal to the length of the graph, then we want to maybe raise an exception, print a message that circle is detected, and once a circle is detected you cannot have a topological order. So you say, let's say raise exception, circle detected, no topological order, right? And then here we just return the ordering. Okay, so attend the live web conference on Saturday mornings for us to have a deeper explanation of all of this in a way that you understand using an app development. We have something we call the Bellman-Ford algorithm that we use when we have negative weight, and when we have a negative weight there, Gstra no longer works, and we find the shortest path from a single source to all other vertices in that weighted graph, even when the weights are negative. So when we have a negative circle, the Bellman-Ford algorithm will also fail, and we are going to look in the next lesson how we can implement that algorithm, how we can see if there is a negative circle, and how we can optimize that implementation before we move on to trying to build a real world app and see how all of this can be implemented in an app. So thank you and see you in the next lesson.